plus B is 2 ones has to be added, and if there is any carryover, that is also available. Okay. So if the first bit x0 is 0, when we add a 1 to it, because for the conversion a 1 has to be added. Okay. So when a 1 is added, then what will happen? A 0 and a 1 will produce an output of 1, and it will go to a place where there is no carry. Okay. So if the initial bit is 0 and if we add a 1, we output a 1 and there is no carry. On the other hand, when the input is 1 and because we have to add a 1 for the XS3 conversion, we will have an output of 0 and remember this carry. So what we do is, from S0, when a 0 occurs as the input, we output a 1 and go to a state where we remember that there is no carry. On the other hand, in S0, when a 1 has occurred, we have to go to a state where the output is 0 and remember that there is a carry. Okay. So on 1 we output 0 and go to a state where we remember this carry. So let me call S1 to be a state which remembers that there is no carry, and S2 to be a state which remembers there is a carry. In addition, we should also remember how many bits we have processed so far, because after getting 4 bits a BCD conversion should be over. We should remember that and go back to the initial state. We should also remember the number of bits processed, because only for the first 2 bits 1 needs to be added, for the subsequent bits zeros has to be added. So we will do the following. So this is the initial state graph which we will put it here. So for S0 we go to S1 or S2. Okay, with these transition, S1 represents there is no carry, so we will indicate it by NC. S2 represents there is a carry, which we will indicate it by C. Now we will look at S1 and then see what happens when the next bit arrives. When the next bit arrives, again we have to add a 1 to that position for an XS3 conversion, and there can be a carry or no carry. Incidentally, in S1 there is no carry. So this is a table we will use for conversion. S1 represents a state where there is no carry. So the carry bit is 0 0, but a 1 needs to be added for the conversion. So that is what this 1 represents. The bit x1 that comes to as the input can be either 0 or 1. So these are the 2 possible cases that will occur. The bit can be 0 or 1, but we know for sure that 1 needs to be added for XS3 conversion, and because there is no carry, there is 0 0. So we will see that for this case, on adding these 3 bits you get a 1 and 0. So we should go to a state where on getting the input of 0 we output a 1 and go to a no carry state. So we will create a new state S3, call it as the no carry state. How do we go? From S1, on getting a 0 we produce a 1 and go to no carry. That is what this transition represents. On the other hand, if a 1 comes, we should output 0 and go to a state where we remember a carry. So for that we will create a new state, call it as S4 and put a C next to it to remember there is a carry state. So on getting a 1, okay, on getting a 1 we output a 0 and go to this carry state. On getting a 1 we output a 0 and go to this state. So this is how we should work at the state S1. Similarly, S2, if you take that one, S2 is a carry state. So we remember carry, so a carry bit has to be added and a 1 needs to be added because it is the second bit in XS3 conversion, a 1 needs to be added, but the bit x1 can be 0 or 1. Accordingly, these 2 are the possibilities. So here we have got 1 1 0 means on addition you will get a 1 0. Here we got 1 1. So what we do is, on getting 0 we produce 0 and go to a carry state. On getting 1 we output a 1 and go to a carry state. So in both these cases we go to a state where we remember carry. So this state already remembers that. So we can as well go to the same state S4. Okay. So on 0 0 or a 1 1 transition we go to S4. See, why we can go to the same state is because all that we remember in S4 is that there is a carry bit which you have to make use of in the next bit processing, and 2 bits have been processed, 1 bit followed by another bit. That is why we use this one. We could not use S2 because S2 remembers 2 things. There is a carry bit and only 1 bit has been processed. This remembers that there is a carry and 2 bits have been processed. So now in S3 we construct a similar table. S3 represents a no carry, so there are 0 zeros, and in the third bit there is nothing needs to be added for XS3 conversion. Already 0 0 1 1, the 2 ones has been added, so these are 0 0. X2, this has to be X2 actually. This X2 can be 0 or 1. Accordingly you will get a 0 0 or a 0 1. So in both cases we go to the no carry state. So from S3 we always go to the no carry state, which is S5. On 0 bar 0 or 1 bar 1 we go to the no carry state. Okay. So here on S4, okay, there can be because there is a carry we have to put a 1 1. No bits need to be added for conversion sake, but the bit can be a 0 or 1. Accordingly we get either a no carry or a carry state. So on a 0, what do we do in S4? On a 0 we get 0, we output a 1 and go to a carry state. That is what this transition represents. 0 we output a 1 and go to the carry state, or a 1 we output a 0 and go to a carry state. 1 we output a 0 and go to a carry state. So again in S5 what can happen is there is no carry because it is a no carry state. No bits need to be added and the bit can be 0 or 1. Accordingly we have these two values. On a 0 we go to a 0 and go to a state where there is no carry. In particular it also note that all bits have been processed, so we as well go to the S0. So either there is a 0 we output a 0 and go to a no carry state which is S0, or a 1 we output a 1 and go to a no carry state which is S0. So from S5 we go to S0. Similarly in S6 we see that, okay, these are two things. There is a carry, there is no bit needs to be added, and the input can be 0 or 1. Accordingly we have 0 1 or 1 0. 0 1 means no carry. So what we do, on getting a 0 we output a 1 and go to a no carry, which should be a reset state also. So from S6 we go to S0 like this one. But if you look at this one, there is a carry that is being generated, but we will see that in a BCD to XS3 conversion no carry will be generated after the 4th bit is processed. So what we conclude here is that this combination will never occur in this state S6. When you are in state S6 the last bit has to be 0. So that is why this condition will not occur. Okay. Having got this Mealy machine like this one, we can then go about constructing the table. This table represents the same information as this graph. What do we do? From the present state PS, we go to the next state for two possible input values x is equal to 0, x is equal to 1, and produce the output Z for two possible input condition 0 and 1. Okay. So from S0, this is S0, we go to, when the input is 0 we go to S1, when the input is 1 we go to S2. That is what we represent it here. On S0, when the input is 0 we go to S1, input is 1 we go to S2. How is the output? When input is 0 we produce a 1, when the input is 1 we produce a 0. When the input in S0, in this one, when the 0 we produce a 1, 1 we produce a 0, 0 we produce a 1, 1 we produce a 0. How about in S1? From S1, based on 0 or 1 as the input, we go to either S3 or S4. Okay, we go to S3 or S4 based on whether the input is 0 or 1. The output produced, for a 0 we produce 1, for a 1 we produce 0. So that is what is represented in these two. How about in S2? From S2 we always goes to S4. For 0 we produce 0, 1 we produce 1. So we have a 0 bar 0 transition, 1 bar 1 transition. From S2 we always go to S4. This is what happens. Okay. Similarly from S3 we always go to S5. That is what this transition, okay, or this transition represents. Again 0, okay, 0, 0 for 0, 1 for 1. That is what this represents. Similarly from S4 also. S4 we either go to S5 or 6, S5 or S6, and from S5 we always go to S0. From S5 we always go to S0. These two. From S6 only a 0 can occur and we can go to S0. From S6 we can only get a 0 and go to S0. The other condition will never occur. So this is the state table representing the state one. Next, what we should do is we can do a state binary assignment for these states, in which case there are 7 states 0 to 6. We could put 3 bits, allocate and encode them as 000, 001, 010 and so on. But this way of arbitrarily assigning states, okay, in an increasing order as we indexed the state may not lead to an optimal realization. So we should try to encode the states in a manner which reduces the realization. For that we have certain guidelines for assigning states, okay. So these are called as the state assignment guidelines. So these are the guidelines. What it tells is, once you have a state table, you follow these guidelines to allocate, encode the states, okay. States that have the same next state for a given input should be given adjacent assignment, okay. For that you have to look at the column of the state. So if you look at this column of the states, states which are the next state for a given state, okay, states that have the same next state for a given state for a given input has to be given adjacent assignment. So you look at the column, look at those states which both of them lead to the same next state for a given input, then they should be adjacent. So if you look for this in this column, look whether there is any repetition, okay. If see here there is a repetition S4 S4, which means S1 as well as S2 are 2 states that go to the same next state, say S4, for the given input x equal to 1. So 1 and 2 has to be given adjacent assignment. We remember that and mark it as a pair 1, 2. Similarly, if you look at it here, these two, okay, are same, which means that S3 and S4 are 2 states which lead to the same next state S5 for a given input 0. So 3 and 4 should be adjacent. That is what the next one indicates. Similarly, if you look at this one, 5 and 6 are 2 states lead to the same next state 0 S0 for the given input, so they shall have to be adjacent. That is the first guideline what it tells. Second guideline tells states that are the next state to the same state should be given adjacent. For that you have to look at the rows. So if you look at this row, states which are the next state for a given state have to be adjacent. So S1 and S2 are 2 states which are next state for S0. So they have to be adjacent. Similarly, 3 and 4 are the next state for S1, they have to be adjacent. S4 and S4 are already the same state, you don't need to worry. 5, 5 is the same state. 5, 6 are 2 different states, but both are next state for S4, so they have to be adjacent. So that is the second rule. The third rule tells that states that have the same input, same output for a given input should be adjacent. So if you look at the output table, this is called as the output table, this is called as the next state table. So those states which have the same output. So if you look at this one, 0, 1 and then 4, 6 have the same output for a given input. So 0, 1, 4, 6 should be adjacent. Similarly, you see 2, 3, 5 have the same output, 2, 3, 5, okay, have the same output for a given input, so they have to be adjacent. We should try to accommodate as much as possible these adjacency. For that we do the following. We construct a form of a state graph and put the states within that as the entries. So what we do is we are going to encode the state using 3 bits Q1, Q2, Q3, and Q1, Q2, Q3 are being put here. So we will try to place 1 and 2 adjacent, 3 and 4 adjacent, 5 and 6 adjacent. One way, see, you know that these two are adjacent, these two are adjacent. One way of easily doing it is to put like this one, 1, 2, 3, 4, 5, 6. They all will be adjacent. But this has been satisfied. But 0, 1, 4, 6 cannot be adjacent in this manner. Similarly, 2, 3, 5 are not adjacent. To satisfy that, what we do is we arrange 0, 1 and 2 here, 3 and 4 here, 5 and 6 here. That way if you do it, 1 and 2 are adjacent, see 1 and 2 are adjacent, we have satisfied is, 3 and 4 are adjacent, we have satisfied it, 5 and 6 are satisfied, and then in addition we satisfy 0, 1 and then 4, 6. See, you see these two are also adjacent. Similarly these 2, 3, 5 are also adjacent, which is also satisfied. So this is a good assignment. If you do so, then the state S0, see, look at this is the state S0. We have assigned Q1, Q2, Q3 are the 3 bits for S0. So according to this one, S0 should have 0, 0, 0. S1 should have the combination, okay, 1, 0, 0, 1, 0, 0. So S1 should be 1, 0, 0, okay, and then this is S2. What is S2? S2 is 1, 0, 1. So what we have done is, here is S2, 1, 0, 1. What you have to simply do is, from this one write down the mapping for S0, S1, S2. For example, S5 has a mapping 0, 1, 1. S3 has a mapping 1, 1, 1. See, look, it is called S3, but we have given a assignment as 1, 1, 1, which you would have normally given only for S7. Okay, so like that. Then wherever S3 occurs here, simply replace it by the corresponding encoding 1, 1, 1. Okay. Similarly, S6 has a mapping 0, 1, 0. So wherever S6 occurs, you just put as a 0, 1, 1 like this one. So this way you construct the state table. Then we have to realize it. Realizing it can be done by constructing the K map for this one. For example, so we have encoded the states using 3 bits Q1, Q2, Q3. So this would be the present state. When you are in present state, Q1, Q2, Q3 will take certain values based on the present state encoding. So that is what is given. So when you are in the present state is S0, where Q1 is 1, Q2 is 1, Q3 is 1. You go to your next state, okay, when the input is 0. According in the next state, Q1 plus Q2 plus Q3 plus will take a value 1, 0, 0. Or for x is equal to 1, they will take a value 1, 0, 1. So this is what this tells. So accordingly, we can construct a K map for Q1 plus Q2 plus Q3 plus and Z and realize it. So what you have to do is, there are 4 inputs, Q1, Q2, Q3 and X. So we need a 4 variable K map. So you can put X and Q1 here, Q2 and Q3 here, find the combination of the X and these 4 and find the corresponding value of Q1 plus and put it here. For example, when X is 0, Q1 is 0, Q2 is 0, Q3 is 0, you will see that this is what represents. So find the corresponding value of Q1 plus and fill it here. In a similar manner, for every combination you have to find and fill this Q1 plus. Similarly, Q2 plus corresponds to the second row. It is present here as well as here, because x equal to 0, x equal to 1 together will represent the value of Q2 plus. So that is found and filled using this one. Q3 plus is given as the last column, these 2 columns, and that is filled here. Z is filled using this one, okay, X, Q1, Q2, Q3. So now you can club these and realize it. You can see that this is nothing but Q2 dash, because all these goes away, this Q2 dash, and this is nothing but Q1, and this is an exclusive OR of X and exclusive NOR of X and Q3, and this is the value of D3 by clubbing these things. Now realizing it is easy. So this is the realization of the machine. There are 3 flip-flops, one for Q1, another for Q2, another for Q3. The output are Q1 Q1 bar, Q2 Q2 bar, Q3 Q3 bar. The input are the D Q1, D for Q2, D for Q3. Common clock goes for all of them. So from the K map we found that Q1 plus, which should be the D input for the Q1, D1 should be Q2 dash. So you just connect Q2 dash to directly to the D input of Q1. You can get Q2 dash from here and connect it like this. Similarly D2, which is Q2 plus, is Q1. So you have to connect Q1 to the D input of Q2, and Q1 you can take it from this and connect it like this, and Q3 is given by this complex equation. You can realize it. We need the term Q1 Q2 Q3. See here Q1 Q2 Q3 are being ANDed. See, don't worry about these NAND gate, assume these 3 to be AND and these to be OR. Okay, what we do is we are ANDing Q1 Q2 Q3. Here what are we doing? We are, X is available, the input is available, this is X bar after a NOT gate, X bar Q3 bar Q1, X bar Q3 bar Q1 is available, X Q1 Q2 bar, X, okay, sorry, this is Q1 bar Q2 bar, Q1 bar Q2 bar is available. So we call these as terms A1, A2, A3, then we OR it. See, actually these are 3 AND gates followed by an OR gate, but we know that an AND OR implementation can be replaced by a NAND NAND implementation. That is why these 2 are implemented as 2 all NAND gates. Similarly, the output Z is nothing but X Q3 plus X bar Q3. Again we have realized it like this one, from X and Q3 bar X bar, we have used it to realize Z. So this is simply a Moore machine which is converts from a non-return to 0 NRZ to the Manchester encoding. So here what happens, we have a sequence of bits 0, 1, 1, 1 zeros and so on. Okay, in this Manchester encoding what we do is we have to have a conversion from a 0 has to be converted from a 0 1, a 1 has to be a 0 bit is encoded as a 0 followed by a 1, the 1 is encoded as a 1 followed by a 0 and so on. So okay, so to do that one we use this kind of an encoding technique. Okay, we will not just get into the in order to save time I will just not get into the corresponding encoding one. The corresponding Moore machine can be obtained like this one from S0. Okay, when you are in 0, okay, when a 0 bit comes, it has to be, you use a clock period which is twice the frequency and view it during the first half of the clock period and the second clock of the half period as a 0 followed by a 0. A 1 is viewed as a 1 followed by a 1. So when a 0 followed by a 0 occurs, you have to produce a 0 followed by a 1. A 1 followed by a 1 occurs, you have to produce a 1 followed by a 0. So this is the basic conversion. So at the beginning of a bit conversion, when a 0 occurs, you go to a state where you produce a 0. Again there has to be only a 0 because it is a 0 bit. So you go to a bit where you produce a 1. So this is a conversion of a 0 bit. Again if the bit 0 occurs, it will be a 2 zeros, bit 0 correspond to 2 zeros. So you go to a state where a 0 is produced followed by a state where a 1 is produced. Similarly in this state, when a 1 is bit 1 comes, there will be a 1 followed by a 1. We have to produce a 1 followed by a 0. So a 1 followed by a 1 occurs, you go to a state where you produce a 1, then go to a state where you produce a 0. Okay. Similarly here, when a 1 occurs, bit 1 occurs, there will be a 2 ones in 2 clock periods. Say a 1 followed by a 1, then you go to a state where you output a 1 followed by a state where you produce a 1. So we can construct a similar state table for this. Well, now comes the important concept of reduction of the state table. So when you construct a state graph and a state table, there may be many states. The lesser the number of states, it leads to lesser reduction, so we need to reduce it. Two techniques are there, one is by row reduction, another is by using implication table. Let us say we want to a sequence detector which can detect a pattern either 0101 or a 1001. How do we construct a state graph or a table for that? So we use this kind of a table, we don't worry about the number of states and so on. We produce as many states as you want, okay, based on the different possible input sequence, and finally feed the functionality of the sequence detector and then reduce the state. So this represents the input sequence that can occur. First bit can be a 0 or 1, then the second bit can be again 0 or 1. Accordingly, the 2-bit sequence can be take 4 possible combination. After getting the third bit, the 3-bit combination can be 8 possible combination. What we do is we just follow this input sequence for all possible cases. We go to different states. Let us say we are in a state A where there is no input bit. When the first bit comes, 0 comes, let us say we go to a state B. When a 1 comes, we go to a state C. Okay. So when in state A, when a 0 comes, we go to B. When a 1 comes, we go to C. This is what we do. In the state B, again a 0 can come or a 1 can come. In state B, when a 0 comes, you go to a state. In B, when a 0 comes, you go to a state D. When a 1 comes, you go to a state E. In the state C, when a 0 comes, you go to a state F, or you go to G when a 1 comes. So like that we have done. See, what we have to do is only after producing after getting all 4 bits, at the end we have to produce a 1 if one out of the 16 possible cases, only if one of these 2 cases occur, we should produce a 1 at the last bit. That is the requirement. So what we do is we wait till all these bits have been obtained and decide whether to output a 1 or not. Now we have these cases. After getting 2 bits, we can be either in D or E or F or G. So far 2 bits have been obtained, accordingly we have gone to D, E, F, G. The third bit can be a 0 or 1. If a 0 occurs in D, let us say we go to H or I based on 0 or 1. Similarly in E we go to J or K, in F we go to L or M, and G we go to N or P. So what we have done is we have not bothered about generating new states. Conveniently we have generated lot of states. Up to now only 3 bits have been obtained, so the output still remains as 0. Now the 4th bit comes. Here after getting 3 bits you can be in 8 possible states, which can be from this one H onwards to P. Now the 4th bit can be 0 or 1. Now if a 4th bit comes, okay, always we should complete the cycle and go to the initial state A. So for all these cases, whether you get a 0 or 1, you always go to A. But your output will be 1 whenever this pattern has occurred. So let us see when that it occurs. See, when you are in 0, 1, 0, when you are in a state 0, 1, 0, and if a 1 has occurred, you should output a 1. So in 0, 1, 0, when a 1 has occurred, we will output a 1. So this is a place. Similarly, the other one is whenever you are in 1, 0, 0, when a 1 occurs, we output a 1. So whenever you are in a 1, 0, 0, when a 1 occurs, we output a 1. So only in these 2 cases it has to be 1. So this way you construct a state table. It has a large number of states, which is not an optimal one. Now we will reduce it. How do we reduce it? We will look for what are called as equivalent states. 2 states are said to be equivalent if on getting the same input they go to the identical state by producing identical output, which means that their behavior is same, so they are equivalent. You don't need 2 separate representation for it. So here if you look at H and I, on getting 0 or 1 they go to AA producing the same output. H and I, their pattern is the same. So you don't need a separate states H and I, they can be the same state. If you, from that you can see that H, I, okay, J and K are different, okay, J and L are different, K, M, N, P are all identical. So instead of this you can retain only one state. So what we do is, let us say we retain H and remove I, K, L, M, N, P, okay, I and then like that one, I, L, M, N, P. So we strike off all these things, wherever I occurs we replace it by H. As we will see, wherever I occurs we have replaced it by H. Similarly M and P, wherever M occurs we have replaced it by H, N also as by H and P also by H. Similarly we find that these two states are identical, that is J and L. So we will, let us say we will remove L and retain J. So wherever L occurs we will replace it by J. Here wherever L occurs we have replaced it by J. J we have retained as it is. Okay. Next what we do, again we look at these and see whether further reduction is possible. So here we see that these two are HH, okay, and these two are also HH. So these can be removed, C can be removed and we can retain only D. So wherever C occurs we have to E occurs we can retain is at D. That is what we have done here also, and like that we have done, we have reduced further states. Finally after reduction we can come with a compact state table where A, B, C, D and E, H, J only alone has been kept, and there after reduction the next state and the outputs are given here. The corresponding state graph is given here, okay. So from A what we do, based on the this one, when there is a 0 you output a 0, when a 0 we output a 0 and go to a state B or B, okay. From A we go to B or C, from B we go to D or E, from C we go to E or D and so on. So from E we go to J or H and so on. So accordingly the state graph has been constructed. So this is what is called as a row reduction technique, okay. So what we will do is we will, okay, that is we will stop at this point. There are just two more advanced technique of row reduction which I will take it in the next the last lecture, and then we will discuss the further aspects in the last lecture. Now I will open it up for any chatting or any doubt clarification session. You can post your question or interact with me using audio or video. So there are some set of questions that have been posted. I will read it out and then try to answer your questions. Why do we need to check 101 in the sequence of a mission? That is just an example. For example, you have a problem. See, basically a digital machine is a binary number manipulator. All problems can be eventually converted into a binary number manipulator or a detector, okay. For example, there may be a condition of we want to check whether a particular condition in a process plant has been met, okay. So that if you do a measurement and produce a sequence of output of a transducer, okay, a pattern may represent a case which needs to be handled, okay. We have taken a simple case that if the sequence is 101 we need to take an action. So that is how we treat the generic problem and look for designing sequence detector. Can we design and synthesis the circuit with the help of standard sequential machine model? Yeah, that is what, whether if there is a sequential circuit to be designed, you can always view it as a finite state machine and follow the same procedure that we have encountered and do it. That is, come up with the state graph, then come up with the state table, use a good state assignment, and then realize it using either D or T or JK flip flop. Why are we using flip flops in the feedback of FSM? As I mentioned, finite state machines, okay, are the machines which remember the state of the circuit and responds differently at different states. So it has to remember the history of the input sequence. So we need memory to remember the history, and therefore we need flip flops to store the memory. What are the difference between state table and the excitation table? See, there are two things. One is the truth table and another is the excitation table. If you look at the flip flops, okay, the truth table gives for a given present state and the given input what would be the next state or the next state of the stored in the flip flop. If that is given, that is called as the truth table of the flip flop. In the case of an excitation table, we decide the excitation to be given to the flip flop for the desired transition to occur. For the given input and the desired next state bit to be stored, what should be the input to the flip flop? That denotes the excitation table. Is there finite changes? Is there finite change in FSM? Yes, a finite, yeah, that is for every state it goes through a finite number of transition and reach other states. Why do we use serial input and serial output circuit? See, that reduces the number of, for several reasons. Once, the complexity of the circuit, okay, can be reduced because the number of input it take and the number of output it gives out is reduced, so the complexity is reduced. Or the requirement may be, as soon as the LSB of the BSD has come, we want the LSB of the XS3 to be available. If that is the, we don't want to wait for all 4 bits of BCD to be available for the conversion to begin. If you do so, we have to collect all 4 bits, wait for the conversion and then again produce it. Again during that time the next set of 4 bits may come. We don't want a delay. So bit by bit, as and when the input comes, we need to produce the output. That may be a reason why a serial input, serial output devices are better. Okay, same thing I have designed. It parallel to parallel may be easier, but there may be certain cases where a serial to serial conversion is what is required. Which flip flop gives the better performance in an FSM? It's not the JK flip flop based realization leads to lesser gates, okay, when you comes for actual implementation. Although the design is complex, JK flip flop based implementation gives better compact circuit, but the performance means that how fast it is depends again maybe on gate, again in which term JK may give a better performance also in terms of the speed. What are the applications of FSM? FSM is a way of representing digital circuits and realizing digital circuits. That is the application. What are the maximum number of states in an FSM? There is no limitation on the maximum number of states. As long as you can handle the complexity, you can have any number of states. Is there any comparison between register and FM? I don't know what you mean by FM. Registers are a set of flip flop storing bits, okay, but finite state machines, they have a register which stores the state. In addition to that, it also changes the state based on the input and output, but registers simply store the bit whatever that we want to store. So every finite state machine has a register, but a register alone cannot be a FSM. How can we design the number of states in synthesizing FSM? It's a good question. As I mentioned, you draw the state graph, reduce it, find the minimal number of state it requires, okay, then if find the minimum number of bits that are required to encode it, okay. For example, if you have FSM with 7 states, you need minimum of 3 bits, 8 states 3 bits. The moment it becomes 9 states, you need to go in for 4 bits because 3 bits cannot occur. So in principle, if capital N represents the number of states. You should take log n to base 2 and then take the ceiling of it, okay, in order to decide the number of flip-flops that you have to use. Is there any other question? Let me just go through these questions. Why were we using flip-flops connect input and output? Why we are using flip-flops connect input and output? The question is not clear. We take the output of the flip-flop and use it for the functional realization, because the next state is dependent upon the present state and the input based on some functionality. That is why there is a feedback. What is the difference between state diagram and state graph? There are no difference. There are two terminologies, they mean the same. Then Sundareshwar and so on. For designing sequence generator, which model can be preferred, Mealy or Moore? As I already answered the question, there are two different, both can be used. Any one of Mealy or Moore machine can be used. It's your choice. For a particular problem, whether the model Moore or Mealy is fixed or different. Again, it is up to you. You can either go in for Mealy based realization or Moore based realization. If the design specification tells that as soon as an input law bit comes, immediately if you have to respond, then you have to go in for Mealy. If there is no such specification, you can either go in for a Mealy or Moore based approach. Why don't we use the excitation table in D flip-flop in FSM synthesis? Okay, for the case of the D flip-flop, the excitation table is very simple. The output of the flip-flop has to be the D input. So whatever the D input of a D flip-flop is the same as the next state value. So dA is equal to A plus. Okay, so it is very easy, you don't need a separate one, because it has got two separate inputs J and K, okay, and we can conveniently change both these things, whereas in D and T there is only one input, so there are two possible inputs that you can give. So based on that, okay, to go some of the terms as we saw in JK1, okay, some of them are don't cares, either in the JA or KA table there are half of them are don't cares. Whenever we have a don't care terms, lot of don't care terms in K-map, the resultant function will be minimal, because you can have a larger square and leading to reduction or removal of more variables. That is why it is compact. Or in the next lecture would be as follows. We will complete the state reduction technique and then equivalent state machines. Then we will see the ASM chart based realization of the digital circuits, okay. Then we will also quickly look at the VHDL model, okay, for flip-flops. Then we will see little bit, if time permits, on asynchronous circuits, and also we will take an example of a traffic light controller and then see how it can be built using digital circuits. There are two more questions. Why do we go row wise while reducing the number of states in designing the sequential circuits? Yes, by looking at two rows, if two rows are identical in the state table, then those two states are equivalent. That is why we do that one. It is also called as the row matching method. What is the difference between synchronous counter and FSM? As I mentioned, synchronous counters are special kind of finite state machine which doesn't have any input or output. That is the only difference. What is the use of sequence detector in FSM synthesis? Now, sequence detector is one way of posing a generic problem, okay. Many problems that occur in nature can be treated to be nothing but detecting of a sequence in a bit pattern. That is why we take sequence detector as a particular case and understand sequence detector synthesis. So we will stop at this point. Okay, thank you.